Good evening and welcome back to Chapter 6. Tonight we'll be looking at how molecules are actually positioned in space. So they don't lie in this two-dimensional world, but a three-dimensional one. So we will use their Lewis structures and your orange papers to help us draw these 3D shapes. So when we draw these 3D shapes, it's called molecular geometry. Or better yet, the Vesper Theory. And what does Vesper Theory state? It is the repulsion between valence electrons that make atoms situate as far apart as possible. So basically, valence for your V, shell, meaning we're looking at our outer shell, electron pair repulsion. So the repulsion between valence electrons. Valence, of course, being your outermost electrons. So shapes, when we start looking at shapes, we're going to depend on both their lone pairs and those shared pairs. Lone pairs would be those extra dots around our elements. Shared pairs are ones that connect two elements together. Big thing here to remember is that our double and triple bonds are treated as a single bond. And finally, we're going to briefly talk about hybridization. Hybridization is just when orbitals are overlapped. So of course, if you're going to have some bonding, you're going to have some sharing of electrons, you're going to have orbitals that are overlapping. And which orbitals overlap depend on the number of electrons around our central atom. Okay, now it's time to take out those bright orange sheets that you have, and we are going to be looking at the other side, so the side with all these silly shapes. From what you can see on this sheet, these are the shapes that we are going to talk about. But today we are going to focus on just the S and P hybrids. So we're going to look at just those valence electrons. We're not going to go any deeper into the D shell today. So a little bit about what you are seeing on your sheet. Of course, yours are not moving around and look very pretty as they do here. So we are going to talk about if we have two pairs. Well, you say, well, what about if I only have one pair? Well, if you only have one pair, you really don't get anything different than also a linear, because you're going to have a molecule attached to a molecule, and the only shape you can have is something that is linear. So let's start with something that is two pairs. So we're going to have S and P overlapping. If you had one pair, it's just going to be S overlapping. So we have two pairs, we have S and P, we have two bonds, and it's going to make a linear molecule. Let's move on to three pairs. In three pairs, we have our S and then two of our P orbitals that are going to overlap. So we have three pairs that we can bond with, and the first one we only make two bonds. So you can see up at the top there, or as it's moving around and maybe on the side or bottom, it's got a pair of dots. Those are lone pairs. So those are ones that are unbonded. The bonds, of course, then are your straight lines. So if only two of our three pairs are bonded, pairs meaning electrons, we have a bent shape, a bent 120. The 120 is just the angle then between the two outside elements. Then we have three pairs, and we can have three bonds in which they are all bonded, and we get trigonoplanar. So these just mean that if you kind of drew a line between all of the outer, you'd get a triangle, and it is all on the same plane. Now we have four pairs, so we have our S overlapping with all three of our P orbitals. So just like before, we can have some that are bonded and some that have lone pairs. So if we have two bonds, we have something that is also bent, but you'll see they are much closer together, and that is because of those two pairs of electrons at the top that are unbonded. Then we can get three bonds, and now we get something that's trigonal pyramid. So we're no longer planar. We have a little bit of bend to all of our atoms, so we get something that is a trigonal pyramid. And then we have 4 pairs. So we get all of them bonded, and we take on this tetrahedral shape. So now let's look at predicting Vesper shapes. When we start predicting Vesper shapes, we need to start with Lewis diagrams. So remember, this is where we find out how many electrons are in its valence shell, and we put them in a pot and then distribute them. So let's start with hydrogen. So hydrogen gives us 1 electron, however we have 2 hydrogens, so it gives us a total of 2 electrons. We're going to add that to our sulfurs, which give us 6, because remember they are in group 16. However, we take off 10 when we're in the P block. So 2 plus 6 means we have 8 electrons to work with. Now we're going to build our shape. So we have hydrogen, and then remember we can't attach hydrogen in the middle, so we're going to attach it to sulfur, and then we're going to attach another hydrogen. So now we have made 2 bonds. Each bond is made up of 2 electrons, so you can think of like 1 from each. So we're going to subtract out 2, 4. So that means we have 4 electrons back in our pot. Hydrogen isn't going to get any more dots, so our dots have to go on sulfur. And we have used up our 4 electrons, so we are down to 0. Now we make sure everything has an octet. So hydrogen is happy with 2. It has its octet, so to say, even though it's not an octet, it's happy. And sulfur has its octet, 2, 4, 6, 8. So everything's good. We don't have to do any extra bonding within this molecule. So now we're going to look at this. When we look at this, we want to know how many bonds have we made and how many pairs of electrons do we have. And this is all around just the central atom. So this is called our central atom. We only care about what is going on that central atom. So it doesn't matter if we have extra electrons around hydrogens, which we won't, but it doesn't matter if we do as we get into later ones. It all depends on this central atom. So if we start looking at pairs of electrons, we've got 1 pair, 2 pairs, 3 pairs, 4 pairs. So we've got 4 pairs. How many of those are bonded? Well, I've got 1 here and 1 here, so I have 2 bonded. So now you're going to look on your orange sheet, and you're going to look at the side that says pairs and look at the side that says bonds, and you're going to see where pairs and bonds intersect. And if you take down or across 2 pairs, or sorry, 4 pairs, 2 bonds, you're going to get bent 105. So you'll have sulfur, your electrons kind of off to the side, and then your hydrogens down here in this bent type shape. Let's try another one. CCl4. So carbon gives us 4 electrons. Cl gives us 7 times 4. So now we have 28. So we have a total of 32 electrons. First one is C, so we're going to put C, and we're going to attach then our 4 Cl's. So now I've got 2, 4, 6, 8. So I subtract my 8, and I am at 24 electrons. So now I'm going to put 24 dots starting around the outside. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So there's all 24. I have used them up. So now make sure everything has an octet. Well, since all the CLs are the same, I'm just going to look at the 1, and that's an octet. And then my carbon, my central atom, has 2, 4, 6, 8. So it's got its octet, and everything is happy again. So again, off of our central atom only, we're going to look at bonds and pairs. So pairs of electrons, I have 2, 4, 6, 8. Oops, sorry, I have 8 electrons, but I have 4 pairs. And bonds, I have 1, 2, 3, 4. So I am going to look on my orange sheet and line up where 4 bonds and 4 pairs meet, and I get a tetrahedral shape. Now, when you look at that tetrahedral shape, I have some funny lines going on. So I would put C, Cl up, and then I have these arrows coming off to my other Cl's, and then I have a dashed line to one more. Well, look, we have a 2D, and it's hard to draw a 3D. So anything that's a single line is in the same plane as the element it is attached to. Anything that's a triangle, you can think of it as coming out at you. So it is coming out of the screen, or it's coming out of the paper at you. And that means our dashed line goes behind. So this would go behind my screen, or go behind your paper. So of course that's hard to show. So this is how I've chosen to show it. So triangles coming out at us, the dashed line, and it doesn't matter how many dashes are in the dashed line, and there's no significance to that. Dashed line means it's going back. So it's just a way of drawing 3D in a two-dimensional space. If you have a better way to show me, have at it. So let's look at CO2. So C gives us 4 electrons. We're going to add that to O2, which O gives us 6. Since we have 2 of them, we have 12. So 4 plus 12 gives us 16 electrons. So we're going to put C in the middle and attach O's to it. And 2, 4, we're going to subtract 4 because that's how many we used to bond. So we're back down to 12 electrons. Now those 12 electrons need to go on the outside first. So 2, 4, 6, 8, 10, 12. Checking for octets. Oxygen is good, but carbon is not. So we remember, if we do not have an octet around our central atom, we steal from, or I guess we share from the outer elements. So I'm going to take 2 from my oxygen and move them to the middle and make a double bond. And because both of these are CO, I'm going to try and keep it as equal as I can. So I'm going to take 2 from my other element, or my other O, and I'm going to have 2 double bonds. Now carbon does have 2, 4, 6, 8, and it has its octet, and we still have 2, 4, 6, 8 for the oxygen. So now everything is happy. So I've used up all 12 of my electrons. So now we're going to start looking at the shape. And we need to figure out, once again, how many bonds and how many pairs of electrons. Now, if you remember back to the very first slide, we said that double and triple bonds are going to count as a single bond. So basically, these are going to be big, fat, single bonds. So we're not going to think of them as 2, we are going to think of them as 1. And a single bond gives us 1 pair. So around carbon, I have 1 pair, 2 pairs. So I have 2 pairs, I have 1 bond, 2 bonds. So I have 2 bonds. So something that is 2 bonds, 2 pairs, gives me a linear shape. So this would stay linear. And that is how you predict your molecular geometry. In class, we will be working on a lab, and you are going to actually be building some of these molecules and seeing them 3D for yourself. So good luck, and make sure you ask questions.